So this where we were. So this is going to be MOS lecture 5, isn't it? Up to 4, I think we covered, isn't it? So 26th April. Today is what? 27th, right? Yeah. So I think. So if we saw what we were discussing in the previous class, I intended to write v equal to 0 here instead of v greater than 0. Okay, so keep that in mind. Maybe I should write this case also phi ms not equal to phi ms less than 0 here. Okay, so so we have phi ms not, and also let me make sure that we explicitly take them one by one. So ideal MOSFET, ideal MOSCAP, we saw that phi ms is 0 and QF is 0, and we independently saw why they have to be so. And in each case, we have derived what the flat band voltage and the threshold voltage. So non-ideal case, we said phi ms is not equal to 0 and QF is also not equal to 0. So to understand phi ms not equal to 0, we have, this is already discussed actually in the previous class, but it was discussed considering QF equal to 0. So I have written this explicitly. Now you don't say this in the video, but I have written it, so it will be appearing in the notes. So phi ms not equal to 0 and say QF is equal to 0 still. So we proceeded forward and we drew band diagram and showed how for phi ms not equal to 0 and even at v equal to 0, the semiconductor bands will not be flat. All right. So if the semiconductor bands are not flat for v equal to 0, then it is non-ideal. So this is how phi ms not equal to 0 will lead to some band bending and some charge in the MOS junction. And we have seen what should be VFB, and we found that VFB has to be phi ms. So phi ms is the voltage that you should apply across the MOS cap and to actually make bands flat. And we have stopped here. You know, we derived expression for VT. We said VFB is phi ms and VT is so and so. So today's lecture, so continued, the phi ms not equal to 0 case is continued. And so I have just I have uttered, I just wrote here, so no need to read it out again. So what we are trying to see is V equal to VFB equal to phi ms less than 0 is the voltage you should connect across the MOS cap so that bands will be flat in the semiconductor. So that's what the meaning of flat band is. And let us see how bands become flat. We saw for V equal to 0 how bands are not flat. Just the previous page band diagram. So for V equal to VFB, which is equal to phi ms, how bands become flat is what we are seeing here. So here the SM junction phi ms is not equal to 0. So we have some band bending, and this kind of band bending arises for phi ms less than 0. So since this is the difference that we are showing between the E naught of semiconductor and metal, that is this difference, which is the Fermi level difference, because built-in potential is always equal to Fermi level difference. So the Fermi level difference is nothing but the work function difference. So Q times mod phi ms, because phi ms is less than 0, I have indicated with mod, because this is only the difference we are showing. Now on the left, this is EF2 of the Fermi level, EF2 of the metal on the right hand side, and the same metal is there on the right left hand side, but with a potential difference of phi ms. How the potential difference can be seen in the band diagram. So if we have phi ms is less than 0, which is what you are applying, so this is at a negative potential than this. So electron energy will be higher in metal on the left hand side compared to on the right hand side, because applied voltage is negative. So phi ms is less than 0 in our example. It is not always so. If phi ms can be greater than 0 also, but in our example it is less than 0. So negative voltage applied to the gate, left side metal, so electron energies should rise, and the Fermi level difference will be equal to applied potential difference, that is equal to Q times mod V. I have written mod here. So EF1 minus EF2 is Q times mod V. Okay, so if this is equal to Q times phi ms, which means this E naught and this E naught should be aligning, because this E naught of semiconductor, E naught of metal on the right hand side, they are separated by Q phi ms. And this E naught and this E naught also should be separated by the same Q phi ms, because EF1 and EF2 are separated by the same Q phi ms. Okay, so definitely E naught has to be matching with semiconductor E naught. So overall E naught has to be flat here this way. Okay, so note that there is a Fermi level difference between MOS, I mean M and S, but still there is no charge transfer because there is oxide. So as if this MOS are isolated now. Okay, as if they don't interact at all, because that you have cut off by applying a voltage. So indirectly you can see it that way. So coming to QF equal to 0 case, and let us say phi ms is 0, just to understand things one by one. So what is this QF? It is called fixed charge. It exists at the oxide semiconductor interface and it is always positive. Okay, so fixed charge is forming actually due to during the oxide growth. We have told that oxide is grown thermally on semiconductor for gate material. So I mean, those details are necessary for this course, but it is understood that during the oxide growth, it is sufficient to understand that during the oxide growth, this positive charge comes, okay, because of chemistry. And it is not just that only positive charge comes, because overall when you finish oxidation, the device has to be taught as a charge neutral. So by the time you grow this oxide, there you will have to have some negative charge here, so that both oxide and semiconductor put together, they should be in neutral. They should be neutral. So if QF is the fixed oxide charge at the interface, then there will be negative QF charge in the semiconductor. So that is how semiconductor charge is not zero. All right, that's what I have written there. So there exists minus QF. Okay, fine. Now what you have to do is, so there exists minus QF charge in semiconductor, hence it is non-ideal. Now to make bands flat in semiconductor, okay, because this minus QF charge comes in semiconductor only due to band bending. All right, so to make bands flat, what you should do, you should remove this negative charge. Okay, you should shift this charge. Okay, our structure is something like this: M, O, S and M. All right, okay, so you should not have and first of all, there are no charges in this SM junction because phi ms is assumed to be 0. So there are no charges in the right hand side metal semiconductor junction. Okay, so there is no potential drop also. No charge, no potential difference. Phi ms is 0. Now there is charge X oxide semiconductor interface charge, and there is a negative charge in semiconductor, and we have to apply VFB such that the charge, there should not be any charge on the semiconductor, in the semiconductor. Okay, so now, which means what, the semiconductor drop is also 0. That's what I have written here. Okay, the semiconductor drop is 0 and this drop also is 0. There is no drop across metal semiconductor junction. Phi ms is 0. No drop in silicon semiconductor. So whatever is the applied voltage, it has to drop across oxide. So that is one point to be noted. So it has to entirely drop across oxide now, you know. And then you know that there is a fixed oxide charge QF here, positive. So if only there is a field due to this QF going towards right side direction, it has to terminate somewhere. And you cannot have field in semiconductor, because field in semiconductor means bands will be flat. So the positive interface charge, okay, its field should not come to the right side. So how can that happen? If you have a positive plate like this, it has field in both directions like this. Okay, if there is a positive plate, you don't want to have this field going to the right hand side. So what will you do? What will you do? Can any suggestion? Hello. So there is a positive sheet charge. Because of it, there is a field going both directions. You know that, right? Positive charge sheet means you have solved it in JE. The field will be sigma by 2 epsilon on both sides. Okay. So now I don't want to have one field in this direction. So I should have all field lines due to this positive charge only in one direction. What should I have then? What should I keep? Simple electrostatics problem. There is sigma here on this. Can somebody answer? Why is there a difficulty in this problem, this simple problem, simple question? Akash Reddy. Advit. Okay. Shrikar.
Yes, sir.
Yeah. You know the question?
Yes, sir.
So, okay. So he has muted. Interesting. Abhimanyu. Okay. Supriya. So you are not there, or you don't want to unmute? Yeah, maybe I should ask this way. Okay. I don't know if you guys really are there, or just logged in and left. Okay. Osama.
So
Yeah, please.
we put negative charge on the other side, then electric will be that.
Yes, that's very good. Yes, that's what I was expecting. It's a simple thing. Okay. So field, if you don't put any negative charge, field will be going till infinite. Okay. So in both directions. Okay, but you don't want to have field in one direction. So you put a negative charge sheet, negative charge sheet with minus sigma, so that all field lines come and terminate on this, because you have sufficient charge minus sigma to compensate for the positive sigma on this right side charge sheet. So all field lines come here. Or in other way, you can think this way. So there is a field this way, both directions field is there. I don't want to have this field. Okay, right side field. So what should I do? A positive charge sheet gives me field this way. So if I put a negative charge sheet here, okay, so this will have a field in the opposite direction, right? This negative charge will cause field in the opposite direction. So in this direction, in this region, it will cancel. Field due to plus sigma and field due to minus sigma cancel. So that's how I can imagine things. And this field gets doubled. And field in this region also, they cancel minus sigma by 2 epsilon and plus sigma by 2 epsilon. They cancel on the region to the left of minus sigma also. So this is what I was expecting. Okay. So you don't want to have any field in the semiconductor. So entire field should be in the oxide due to that plus QF. So you should have a minus QF on metal. Okay, so that much of charge if you supply from battery, okay, so you are going to have field only in the oxide and not in semiconductor. What indirectly you are doing is you take this MOS junction, okay, you put metal and metal all that, and then this negative charge, you apply a battery. What it does, it just take this negative charge and puts it on the metal. That's what it does. That's what this battery does. All right. So now what should be the voltage? Now it is simple. So this is what I have drawn here. Entire field should be actually terminating on the metal. And if you have a plus QF charge here and minus QF charge here across two plates of oxide, we know that drop across oxide will be minus QF by Cox, because that is the charge on the oxide plates. Okay, two sides of the oxide. So minus QF by Cox, we have seen that. Okay, or it is just like oxide capacitance. Q by capacitance gives you voltage. So that's what we have it here. minus QF because there are negative charges on the left hand side, positive charge on the right hand side, and Ψox is always from left hand to right hand. I mean, this way it is. Ψox is this way, but positive charge is on this side, so you have to keep a minus sign. So minus QF by Cox. And earlier we saw that no drop here in semiconductor and metal semiconductor junction. So entire applied voltage should be Ψox. So VFB should be Ψox, which in other words, VFB is equal to Ψox, and Ψox is nothing but minus QF by Cox. So VFB should be minus QF by Cox. So that's how it is. So non-ideal MOSCAP from principle of superposition, 1 and 2 together give 1 and 2 means what? Case 1, phi ms not equal to 0. This one is QF not equal to 0. So they are independent kind of pictures. So from principle of superposition, you just add, so VFB equal to 0 gives you ideal MOSCAP. VFB equal to phi ms minus QF by Cox. We just added them both. If both phi ms as well as if both phi ms as well as QF not equal to 0. Okay, this is first contribution phi ms not equal to 0. The second contribution QF not equal to 0. And what is VT? So that's what we have to see now. So VT is the applied voltage at which surface concentration of electrons is equal to concentration of holes deep inside. So and then psi s, that point at that threshold, psi s is equal to 2 phi f. We have seen that. And QS is nothing but QD at inversion, and that is nothing but minus root over 2q Na epsilon s. And instead of the psi s will be there in general, so you have to put 2 phi f because it is QD inversion. So Vox equal to Ψox plus Ψs plus phi ms. Ψs is known. Phi ms is something that is that should be given because unless what metal, what semiconductor we are talking about, we cannot calculate phi ms. So phi ms is a given quantity. Ψs we know 2 phi f, which comes from doping of the semiconductor. Ψox is what we have to determine. What is Ψox at threshold? For that we need to find Eox, I mean electric field in the oxide. Again, Gaussian pillbox you take, oxide oxide semiconductor. This is the interface. And now that we have to introduce non-ideal case, there is a fixed charge QF here, and there is some semiconductor charge QS here. So this is QF, and this is QS. All right. So Eox is here this way into the surface. Here E is 0. So surface integral, this one Gauss's law. So the right hand side it will be 0. It's only one-dimensional picture. So curved surface we should not take. Electric field is 0. Electric field is not varying in this direction, vertical direction. It is not there. So Eox is minus this first, only the left thing will be there, minus epsilon ox Eox equal to charge in the and charge enclosed, that is nothing but QF and then QS. Let QS sign will be negative, but the symbol for charge inside semiconductor is QS. If it is negative, then QS will be negative. QF is always positive, we know that. So now that we have obtained electric field inside oxide is QF plus QS by epsilon ox. So indirectly what it means is QF plus QS is the charge that should be on the left hand side metal surface. Okay, so that's what it is. Ψox is now Eox times Tox. So QF plus QS by Cox with a negative sign. So indirectly it tells you QF plus QS is the charge on the metal. QF is and QF plus QS is charge on the right hand side. And the right hand side, this QF is present exactly at the interface. And then this QS second term is present in the semiconductor. And this picture is like there is an oxide and there is one plate like this which has QF plus QS charge, and the other plate is negative charge, and the other plate has some charge right at the interface, and the other electrode is little thick, not like metal electrode, and it has some charge QS. So this side you have QF plus QS charge. Okay, so I will remove all this. It is as if two electrode like this, and you have oxide in between. So that is what Ψox is. always true. This is always true. Okay, we have not used any condition yet. But now at threshold, what is psiox? So psiox at Vt is equal to Qf will not change. Qs becomes Qd inversion because it is threshold. Qs is equal to Qd inversion by psiox. All right. So minus Qf by psiox and plus this minus pushed inside minus Qd inversion by psiox. Thus, from V, this is which is valid for valid in general. V equal to psiox plus Is plus phi ms. You substitute psiox here, and the psi-s is 2 phi f phi ms. So now, if you combine this term and this term, minus Qf by Cx plus phi ms separate, and minus Qd inversion by Cx plus 2 phi f, you see that this term is nothing but VFB. And this we have seen it for Vt ideal. So ideal MOSCAP, this is Vt ideal, and this is VFB. So Vt is basically what? We take Vt ideal and then add VFB to it. Okay, so it is as if entire voltage axis is getting shifted by a value VFB. Okay, and where Vt ideal is given, and the Qd inversion I have written it again. All right, so all the formulas are summarized below. VFB ideal 0, Vt ideal is this Qd inversion plus 2 phi f, whereas Qd inversion is given here below and Ciox is given below. So all are per centimeter square units. Okay, Qd inversion is formula is there, Cx formula is there. So the ideal case is done. So non-ideal case, VFB is phi ms minus Qf by Ciox, and Vt minus VFB is Vt ideal again indirectly. So Vt will be Vt ideal plus VFB. So you are just adding VFB to Vt ideal to get Vt in the case of non-ideal. Okay. Maybe I'll write it same. Now QS will be looking what? You know, I told entire thing is getting shifted by VFB. Earlier we were doing it at 0 accumulation and then depletion and then inversion. Now we have to shift that QS to VFB. I have considered VFB negative here because we have phi ms minus QF by Ciox, right? VFB is phi ms minus QF by Ciox. And so far QF is positive, so phi ms is negative, we have considered in our example. So VFB is negative. All right. So I have shifted it to the left hand side, So now CV characteristics. So now that we have understood QV characteristics, charge versus voltage, now it is time to go to CV characteristics. Before we go there, just I'll pause for a moment to see if there are any questions. Okay, I'll proceed. So CV characteristics means we have to define what is the capacitance that we are talking about. So definition is, well, the capacitance we talk about is quasi-static capacitance. Also means small signal capacitance at low frequencies. Okay, low quasi-static, right? So low frequencies. Okay, so low means we will come to that little later. Okay, not very high. Okay, that's what it means, because even in the regime where you can define quasi-static capacitance, there also we talk about the lower frequency, middle frequency, higher frequency, and all that. So even in the region where this capacitance definition is valid, that is like quasi-static capacitance, in that range of frequencies also we have low, high, medium, etc. So it is like very high frequencies, you cannot have this quasi-static approximation. So basically small signal capacitance. And in your next course, analog circuits, you will understand what is this meaning, what is the meaning of small signal capacitance or small signal equivalent circuit, all that, because devices are used in electronics and circuits, and unless the device performance for small signals, you wouldn't analyze circuits. Okay, So what is the definition here? C equal to mod dqs by dv. This is the definition. So which is what? What is this? Modulus of derivative of qs with respect to applied voltage. All right, and this is of interest in our circuit. Okay, so note that it's not same as the familiar C equal to q by v. So this is not same as what we have here defined as quasi-static capacitance. This capacitance is different, like not what you have been familiar with. So what it means is, say a device is in neutral, device is neutral overall, but the charge is Q, which means the battery supplied say positive Q and negative Q like this. All right, and then you have increased voltage delta V. All right, from V to delta V, you have increased V plus delta V. So the charge condition also will change in the device. It becomes Q plus delta Q. So which means what? Q plus delta Q charge went this way. Q plus delta Q with a negative sign went in this way, in this direction. So this is how you have a device with Q plus delta Q charge, but device may be overall neutral. We have seen that earlier. So why this kind of thing is of importance in circuits is, say circuits, they are biased in some range, and then you apply sinusoidal signal and you amplify that. So in mostly electronics, this is what you see. You have a small signal which gets amplified. Okay, that is what this transistor does. Okay, it amplifies signals. So since it amplifies signals, small signals, so you want to understand how the circuit behaves for a small signal. Okay, so how much charge actually only this variation gives you. So this how much this Q changes for a change in V. That's what you will be having interest in. So what it means is you are trying to find out delta Q by delta V. Okay, and this becomes same as C from displacement current. Say now you have V and then Q, then the sinusoidal V which results in sinusoidal Q. So which means there is some sinusoidal current flowing in the device on top of the DC current. Okay, so there is a sinusoidal current flowing in the device, and if there is an offset between V and I, then there will be some capacitance also. Offset means what? In the phasor diagram, I'm saying offset. So which means if I or V leads or lags, you have some imaginary term in the current, which corresponds to either capacitance or inductance. You know that. So the displacement current gives you capacitance, and which is similar to, you have a device and you know Q as a function of V, and then you take derivative, that capacitance will be same as the displacement current, capacitance obtained from displacement current, that you will see in circuits. But why we are interested in this? Just to give you motivation, I have talked about it. So now that we know Qs versus V, we should find derivative and then say that that is what is capacitance, and that capacitance can be used in your circuit when you want to analyze a circuit. So that is why we are interested in capacitance for that matter. So to analyze a circuit having this particular MOS capacitor, you need to understand how this capacitance changes and what bias, what is the value of capacitance, etc. So we want to obtain capacitance versus voltage curve, which is simply derivative of Q versus V. So consider again our familiar three regions: accumulation, depletion, and inversion. And accumulation is this: V less than or equal to VFB. So V is this, we know that. And accumulation, psi s is approximated to 0 because high concentration of holes rapidly falls to 0 at the interface. So it can be treated as, zero potential drop. And the psi ox is nothing but minus Qs by C ox. Okay. So again, here I have not included QF. Okay. So, but if you want to include, you can. So let me include, because let us analyze for general case. So QF plus QS by C ox. Psi ox is QF plus QS by C ox. So psi ox is that, and psi s is approximately 0 plus phi ms. Now if you do derivative, dv is equal to minus 1 by C ox QF will not change. It is fixed charge, so it will not change with bias. So for a dV, what is it? Take derivative. So dV is equal to minus 1 by Cox. QF will not change, so dQs will be there. 0. Phi ms will not change. Equilibrium, that MOS, the metal semiconductor junction, will always be in equilibrium. So now you have dQs by dV is equal to minus Cox. Okay. So what this minus means, you understand this as this QS versus V. If you plot, if you increase voltage, QS is going to become small. So that's what this negative sign is, and the slope is Cox. So the capacitance definition is C is equal to mod of dQs by dV. So we get Cox. All right. So what is the interpretation of it physically? What is the interpretation? So this, let us say this is the space charge density picture, charge picture, metal oxide semiconductor. So you have a charge on inside in the semiconductor, which is QS, and this will be minus QS. QS is the charge in semiconductor, and correspondingly minus QS will be there on the metal. Let us say for now QF is 0. Okay, so that's why QS plus QS and minus QS. Or I can add here QS plus QF. So it's okay. So this is the charge I have, and incremental charge picture, because this is what we are interested in, because our capacitance is related to incremental charge by incremental voltage. Okay, we call it incremental picture. So MOS, and if you have bias delta V, that extra charge, where will it go and sit? So the here once you apply V plus delta V. So this is the charge picture for applied voltage V. If you apply V plus delta V, then there will be a little higher concentration here like this. You know, holes will accumulate further like this. And then this also increases like this. Okay. So this is for V plus delta V. All right. Now, if you see the incremental charge picture, this difference in area gives you, incremental charge delta QS, and it is this way. And here the difference between red and yellow lines give you the difference in charge, that is minus delta QS. And if you see, it appears like the change in charge occurs right on the edges of oxide. So the change in charge occurs at the edges of the oxide. So the capacitance will be seen as oxide capacitance. So that is why, because if you see delta Q by delta V, the change in charge is happening across the oxide edges. So the separation between the change in charge gives you the capacitance, right? So epsilon ox by T ox you do, and that gives you oxide capacitance only. So that's why we have C versus V. If you plot less than V less than VFP, you have capacitance equal to C ox. Okay. So now moving, any questions so far? Any doubts in the discussion so far? Okay. So moving forward, we have depletion, which is from VFB to VT. Voltage ranges between VFB and VT, and that is what is depletion. And V is this. I am writing again and again. So, and psi ox is this. All right. So we know how depletion charge varies with psi s, that is QS equal to QD, because in the depletion I can neglect the inversion charge QI. We have seen that earlier. So QS is equal to QD, which is nothing but minus QNA times depletion width, and minus QNA times depletion width is formula is 2 epsilon s by QNA times psi s. Psi s is the drop across the depletion region. It's a quadratic relation. So you have, simply 2 epsilon s psi s by QNA. So QS equal to QD equal to minus root over 2 QNA epsilon s psi s. And for QD inversion, you just put psi s equal to 2 phi f. That's what we have been doing. And if you express psi s in terms of QS, it is psi s equal to QS square by 2 QNA epsilon s. All right. Now you just write the same thing here. You know psi ox, that is here, and psi s just now we have derived in terms of QS and phi ms. So just put those three. You'll have these two together is psi ox, and this is basically psi s in terms of qs. Now that we have got voltage in terms of qs, let us find qs in terms of voltage. So it is a quadratic equation, and we are simply doing that, simplifying. And you know that minus qf by cox plus phi ms can be identified as vfb. So this is what it is. So this term is here, minus qs by cox is here. V is taken to the left hand side and written like this. Okay. So qs now is minus b, that is 1 by cox here, plus or minus root over b square minus 4ac formula, b square 1 by cox square minus 4ac, there is a minus sign here, so plus 4 times a and c by 2a, 2 times 1 by 2qna epsilon s you get. And since qs is less than 0 for v greater than vfb, we should choose negative sign here, because positive sign means qs will be positive, so that's not correct. So you should choose a negative sign here. So choose a negative sign, and just manipulating this algebraically, you get qna epsilon s by cox times 1 minus root of this. All right, and now you take derivative dqs by dv, you get qn epsilon s by cox and some expression, just taking derivative of this. There's no big confusion. It is minus here, root over x derivative 1 by 2 root x, so 1 by 2 root x. Okay, all right, and then the derivative of things inside. Okay, so that is 2 cox square by qna epsilon s, because v minus vfb derivative is 1. So you simplify it further. So call it C equal to modulus of this, and you have cox by this. And you see that as V increases, C decreases. So V increases means denominator increases. Denominator increases means overall the quantity decreases. So that's what we see. Why is it so? So let us get the interpretation, physical meaning of it. So here is where you have this is qs, this is minus qs, this is space charge picture, and now you have increased voltage v to v plus delta v. So it has increased like this. So here it has increased like this. Now the same thing is shown here. Incremental charge picture is delta q, my delta qs is happening at the depletion edge. Okay, so the change in charge, because this is minus qna, right? this is minus qna. You cannot increase the magnitude of this. You cannot increase the magnitude of this. Already it is complete depletion. You cannot increase the magnitude of this. We are still in the depletion region. So if you increase the voltage, depletion width increases. So this is what it is. Okay, so since the depletion width increases, the change in charge, is happening at xd distance, okay, from 0. It is not happening at the oxide edge, because at the oxide edge, unlike in accumulation, now we have depletion. Oxide edge, we have completely depleted region. So charge here cannot increase beyond this, unless we get into inversion, where electron charge starts appearing across at the interface. Sorry. So we are not beyond inversion. We are still in the depletion region. We are explaining the case of depletion regime of operation. So inversion charge is insignificant. So the change in charge has to come from the increased depletion width. So the change in charge is happening here and on the metal surface. So there is the large separation. Okay. Now as V increases, the depletion width increases. Now this is for a particular V. If I have another V, so let us say the depletion edge will be here. And up from there, if I put delta V, then it will increase to here. So the change in charge happens at larger distance. This is XD1, say, this is XD2. And this is for V1, this is for V2. All right. So at V1, if I have delta V, it happens at XD1. Okay. At V2, if I happen to apply, delta V, then the change happens at, delta xd2, sorry, the change delta qs happens at xd2. So this is what we have to see. So is, you know, that separation between the charges plus q plus minus charges is equal to here Tox plus xd. So Tox is the oxide thickness. Here if you see, this is the separation between the plus minus charges. So here it is Tox plus, this is Tox. Okay, and this is 0. So this is xd. So separation between the charges is Tox plus xd. So larger the charge separation, weaker is the capacitance. From simple formula, capacitance formula epsilon A by D, and you know that D is the separation between charges. Okay, so if charges are separated by a large distance, then capacitance will be small. Now see what is happening. As V increases, XD increases. All right, so Tox plus XD increases, implies C decreases. So that's what we understand. All right, so at V1, XD1 is the depletion width, and for a delta V above V1, the change happens at XD1. And for V2, if for a change delta V above V2, change in charge happens at XD2. So capacitance in case of V1 is larger because separation is smaller, and capacitance at V2 is smaller because the separation between the charges is larger. Okay. So this is the physical interpretation why capacitance decreases in the depletion region or region of operation. Now this is, if this is not enough physical meaning yet, take equation 1 for voltage, which is expressed in terms of Qs in the previous page. All right. Now since Qs is less than 0, let's write this equation as modulus Qs. Okay. So here V is okay. So V is minus Qf by Cox, minus Qs will be plus mod Qs. Okay. And then this is Qs square, but let me write it as mod Qs square. Now if I take derivative with respect to Qs or even mod Qs, what I'll have is, let us say with respect to mod Qs I take, and I still call this as dV by dQs mod equal to mod Qs with respect to derivative with respect to mod Qs, right? So you'll have this one 0. Here you will have 1 by Cox, and here it will have, you will have 2 times mod is mod Qs. So 2 cancel. So mod Qs by Qna epsilon s. And if you see, this is what we have defined as 1 by C. Okay. So C is nothing but mod of dQs by dV. So this becomes 1 by C. 1 by Cox plus, you know that mod Qs is Qna xd. Okay, mod Qs is Qna xd. Okay, Qna is concentration and xd is the width, depletion width. So Qna is there, denominator Qna is there, so they cancel each other. So you'll have xd in the numerator and epsilon s in the denominator. So xd by epsilon s. So what is the meaning of this? So call this xd by epsilon s as 1 by cs. So 1 by c is equal to 1 by Cox plus 1 by cs. So this is basically parallel combination of Cox and cs, where cs is epsilon s by xd is the semiconductor capacitance. You know, you have seen this in PN junction case. Okay, capacitance in PN junction case, you have seen what is the depletion width capacitance. Okay, so this is clearly the depletion width capacitance of semiconductor. Okay, so CS. So it is as if oxide and semiconductor capacitances are in series, because CS is epsilon s by xd. We have seen it in the PN junction case, the depletion width capacitance. So incremental charge picture, now let us revisit. So you have minus Qs here, plus Qs here at xd. All right. So you can actually introduce plus Qs and minus, plus delta Qs and minus delta Qs at the interface charge. Okay. Now combine this as this minus delta Qs here, plus delta Qs. Take these two plus minus charges and they give you Cox. And just on top you have put minus delta Qs. So you are still neutralizing charge. So you have not put extra charge. They will be canceling each other. And this charge and this negative charge These two you take and then call it CS. So you have a COX and then you have a CS. So COX and CS. So they are in series. What I have written here, yeah, capacitance. This is nothing but series combination, not like resistors, right? Capacitance series expression is this.
Sir.
Yeah.
Sir, here you wrote mod QS is equal to QNA into XD, right? So the units are not matching.
Why?
QS is coulombs, right?
Coulombs per centimeter square. I've been telling all this capacitance and charges are in units of per centimeter square, coulomb per centimeter square. Okay, because area, whatever be the area you take. Okay, so from beginning we have been doing that. Okay, because what is the definition of what is COX? Then we have defined epsilon ox by TOX. What about area? We didn't say area, right? COX we have defined as epsilon ox by TOX. So we have not multiplied by area. Normally epsilon A by D gives you capacitance. So epsilon ox by TOX will be in farad per centimeter square units, isn't it?
Yes, sir.
Yeah, and then for voltages, you will not have problem. Voltages, you will not have voltage per centimeter square, meaningless. But wherever you find voltage, you see that you are dividing charge per centimeter square by capacitance per centimeter square. Okay,
Yes,
so that's why that coulomb per centimeter square by farad per centimeter square, you still get voltage. Okay, so things are per centimeter square. Wherever you talk about quantities like things that depend on area. Of course, applied voltage doesn't depend on area. Potential drop doesn't depend on area. Things like that. Yeah. So this is the total picture, total line. So inversion we still have to talk. So C as a function of V, for V less than VFP, we have seen it to be flat, COX, and between VFP and VT, it is depletion and it is decreasing from COX to some value. And what is this value? This is called C min. What is C min? C min will be C at V equal to VT. So just put that here in the expression for C, which is derived here, COX by root over 1 plus 2 COX square into VT minus VFB by QNA epsilon S. I hope I remember. Okay, let me just take this. So here you have VT. You know what is VT, VFP, all those formulas you put and you get C min. Okay, so this is C min. And so this you can clearly see as C min. C min is nothing but C ox, COX series with CS at inversion. Okay, so what is the meaning of CS at inversion? It is CS inversion will be equal to epsilon S by XD inversion. So whatever is the inversion layer thickness, or sorry, inversion layer, the whatever depletion layer thickness or depletion width, XD inversion you put, you get CS inversion. This is easier to calculate because this formula is a single formula. But if you forget, what will you do? You have to go to basics and then do it. What is basics? C min is COX in series with CS inversion. Okay, CS which at inversion. And CS at inversion is epsilon S by XD at inversion. XD inversion, you know, simple formula, that is depletion width formula, at least you should remember, if not this formula. Okay, yeah, and then you just calculate. That's all. So inversion we will talk about in next class. Okay, so I'll take I will do one thing. I'll try to finish MOSFET this week. Okay, of course, waiting for some decisions. So But as per my plan, before any other things happen, as per my plan, I wanted to finish MOSFET, which is very important for your future courses in electronics. You should understand MOSFET well, because that is the device that is sold out the biggest number of the large number of times in world so far. Okay, so not just in electronics. You take any device that is the largest. It is in the order of 10 power 20 or so, things like that. So MOSFET is very important. So I'll try to finish MOSFET this week. And then I wanted to cover, as per my earlier plan. So next week we have only 2 classes, right? So I thought I will just, just outline what is BJT, what is LED, what is solar cell. It is like some TED talk or, what popular talk. It may not be like detailed technical talks and things like that. Somewhat technical, of course, but it is like what minimum you should understand about BJT and how an LED works and solar cell works. These are very, very important devices. So I thought they will be like more of theory or kind of high level talks, not very detailed math involved or anything, just concepts, minimum concepts. So and some questions will come from there, which will be the most easy ones because they are superficial high level discussions. So definitely easier questions can come from them. So that's what I thought will be scoring. And next just 2 classes I'll spend, I thought, but let us see what how we are going to do. But for now, let us try to finish MOSFET this week, whatever happens. So I will send a recorded lecture. Please watch it before Thursday. And with Thursday, Friday lectures online, I'll just finish MOSFET, and that's all. That will be there for mostly for this course. And next week, whatever lectures, it just like for completeness sake. Okay, yeah, and then they will be kind of little superficial or high level, you call it, and we'll see what is going to happen. Things are not that good, very dynamic, and a lot of bad things are happening around. So we have to wait and see. All right. So I'll record just one lecture, watch it before Thursday, and then we will try to finish MOSFET and to justify this course. Yeah. All right. Any questions?